Welcome to our video, Differences between Isoloc IPL vibration isolation plates and IPK vibration isolation packages. What effect does layering IPL to form IPK have on dynamic properties, and how does this benefit you as a user? All Isoloc vibration isolation plates are suitable for vibration, shock, and structure-borne sound isolation. Our vibration isolation plates, based on special synthetic elastomers, are indispensable construction elements in all areas of industry. Information on other vibration isolation products can be found on our website. Today's high-performance elastomers no longer have much in common with the materials derived from natural rubber, which are still frequently used in commercially available rubber buffers. Higher operating temperatures, a wide variety of environmental conditions, chemically aggressive contact media, oils, acids, alkalis, ever faster machines, and increasing demands for efficiency and cost-effectiveness are leading engineers today to turn to synthetic rubber. Isoloc not only uses a single elastomer in the manufacture of its vibration isolation plates, but is also one of the only well-known manufacturer in the vibration technology sector to use different types of elastomers. This enables Isoloc to cover a wide range of requirements and application scenarios. For example, the most commonly used NBR rubber is very oil-resistant, but not solvent-resistant. For such applications, Isoloc uses other elastomer compounds that meet this requirement. So much for the chemical properties and special features of IPL vibration isolation plates. IPL serves as the basis for most of the vibration isolation measures carried out by Isoloc. IPL from Isoloc acts as both a spring and a damper. I would like to take this opportunity to refer you to the explanatory video, Vibration Isolation and Vibration Damping. Differences briefly explained on Isoloc's YouTube channel. The Isoloc IPL plate range extends from very soft to very rigid plates with very high maximum compressive stress values. Effective vibration isolation often requires a low, vertical, and/or horizontal natural frequency significantly less than 20 Hz. With the IPL6, a vertical natural frequency of approximately 17 to 18 Hz can be achieved at a compressive stress of 0.3 newtons per square millimeter. As you may already know or have learned from our YouTube video on amplitude frequency response, when designing a vibration isolation measure, the ratio of excitation frequency to natural frequency is decisive in determining whether vibration reduction can be achieved at all. Let's assume you have an application where the excitation frequency, given by the rotational speed or stroke rate of a machine, is 20 Hz, or 1200 revolutions per minute. A reduction in the excitation forces acting on the substrate at this excitation frequency can only be achieved by means of an elastic mounting if the ratio of excitation frequency to natural frequency is greater than the square root of 2. It follows that the natural frequency of the mounting must be less than or equal to 14 Hz. However, in order to achieve a sufficient reduction, the ratio eta should be greater than 2. As already mentioned, with the IPL6 plate we achieve a vertical natural frequency of approximately 17 to 18 Hz. The IPL6 is therefore not suitable for vibration reduction, in our example with an excitation frequency of 20 Hz. What can be done? This is where our IPK vibration isolation packages come in. IPKs consist of individual IPL plates layered and bonded with GPL intermediate plates. But what difference does this make? How does this layering of individual IPL plates affect the overall stiffness and thus the dynamic properties, i.e., the natural frequency of the bearing? Let's take a look at the curves of the vertical natural frequencies plotted against the compressive stress for IPK62 to IPK66. As you can see, with a pressure stress of 0.3 newtons per square millimeter, we arrive at a vertical natural frequency of approximately 12 Hz for IPK62 and a vertical natural frequency of approximately 5.8 Hz for IPK66. This means that the requirement from our application example can already be met by an IPK62. However, in order to avoid reaching the maximum pressure stress, we recommend designing for a mean pressure stress of 0.2 newtons per square millimeter and using an IPK63 rather than an IPK62. So why does the overall stiffness change when IPL insulation boards are laminated to form an IPK? Put simply, Laminating individual IPL boards with GPL interlayers makes the composite package softer. Let's take a closer look and explain. Physically, the following is behind this. We again consider a single mass oscillator with 1 degree of freedom, a mass m with an equivalent linear spring with stiffness k, the natural circular frequency, and the resulting natural frequency for the undamped case is omega 0 is equal to the square root of k divided by m, and the natural frequency f0 is accordingly the quotient of omega 0 and 2 pi. When several linear springs are connected in series, the stiffness k used in this formula is replaced by an equivalent spring with total stiffness k. In series, the force in all springs is the same, but the displacement components, spring deflection, add up. Each additional spring adds additional compliance to the system. The total compliance increases and the total stiffness decreases. With the same mass, the formula immediately makes it clear that the natural frequency decreases. We now mentally replace the spring symbols with IPL and IPKs, respectively, and obtain the answer to our initial question. Here are some simple formulas to illustrate the physical principle. I hope this information and explanation was sufficient for you. If you have any further questions, please do not hesitate to contact us. Our experts will be happy to help you. In the rest of this video, we would like to mention a few important points that should always be taken into account when designing a system. In vibration isolation elements are often described using a simplified two-parameter model, such as the linear Voigt-Kelvin model, in the form of a parallel connection of a spring and a damper with velocity proportional damping. In the case of elastomer springs, a distinction must be made between different stiffness definitions. See also DIN 1311-2 and VDI Guideline 262-2. At Isoloc, common characteristic values for the descriptive dynamic properties are static stiffness, dynamic equivalent stiffness, and damping coefficient. We must repeatedly point out, and would like to do so here as well, that elastomer springs do not have a linear characteristic curve of spring stiffness, but rather a characteristic curve that is, in some cases, highly nonlinear. This means that the static deflection of an elastomer spring cannot be used to determine the corresponding spring stiffness, and thus the natural frequency with the next higher or lower load. For this reason, we refer to dynamic stiffness. This is determined metrologically for various operating points using appropriate measurement methods. Depending on the elastomer and profile design, the dynamic stiffness can be 2 to 3 times greater than the static stiffness. As a result, the natural frequencies are also significantly higher. For this reason, elastomers cannot be compared one-to-one with coil springs. This must be checked and, if necessary, questioned in the designs or catalog specifications of various suppliers. For the design of vibration isolation measures with elastomer springs, the dynamic stiffness, or, more precisely, the natural frequency determined by measurement, must always be used. At Isoloc, the natural frequency is always specified from the dynamic stiffness. When talking about elastomers, you often hear, we need a rubber spring with shore A 60. Shore hardness A, in the range of 10 to 99, describes how deeply a test needle can be pressed into the material. However, this test is purely static. A defined force is applied, and the resistance of the material is measured. That's it. But when it comes to vibrations, something completely different happens. The component is subjected to alternating loads over time. It vibrates. And this is where dynamic material properties come into play. That is why the following applies when assessing a vibration isolation plate. Shore hardness is secondary at most. It reflects a rough material hardness, but in no way replaces dynamic characterization. The construction heights of the IPK vibration isolation packages increase as the natural frequency decreases, from approximately 33 mm for the IPK 62 to over 100 mm for the IPK 66. These construction heights should be taken into account from the outset in your planning. Our comprehensive technical data sheets for each IPL vibration isolation plate and IPK provide all the important characteristics in a compact format on a single page. This brings us to the end of this explanatory video. We hope you enjoyed it and found it useful. Further information can be found on our website. Under Solutions, you will find many examples from various areas of mechanical and plant engineering where Isoloc technology has been used. Talk to us, we will find a solution for your vibration problem too. Isoloc, your perfection is our goal.